as we had done last time also. Madam, would we be taking questions in between like last time, or would we have a session and then we take the questions at the end of it?
It's up to you. Today's session is not likely to be as long as last time's. I'm going to try and finish in about half an hour. So if you prefer to take questions at the end, I'm okay with that.
Okay. So it's your choice, madam. I think last time format worked well with us, where we finished one concept and we had some questions, and everybody had a very nice time because they could ask questions and then we could go back, revisit a topic if it was not very clear to any of us. So we'll just have that. And before we begin, as is the ritual, we have a small quiz prepared. Now this quiz, actually, I found out some questions and I put it off, and I'm sure madam would help us answer all these questions. So here is the quiz for today. And like before, I request all the participants to please WhatsApp their answer onto this number 9953621242. This is 9953621242, and we request you to send your answers in the format. You write your name, write the name of your institute, and then the answer in one numerical, that is whatever is the right sequence of answers, 1 2 3 4 1. So you just WhatsApp on this number 9953621242. Okay, so here's the question. So the question one is, so it's a little basic one, so this shouldn't be a problem. A type 1 error occurs when, so this is basically a definition of type 1 error. When we reject a false null hypothesis, we reject a true null hypothesis, we do not reject a false null hypothesis, or we do not reject a true null hypothesis. So what is a type 1 error? How do we define a type 1 error? Similar, what is type 2 error, or how do we define type 2 error? When we reject a false null hypothesis, when we reject a true null hypothesis, we do not reject a false null hypothesis, and 4, we do not reject a true null hypothesis. So just the two errors that we wanted to cover, type 1, type 2. Okay, so a longish question. How do we define p-value? So p-value of the test is, it is the smallest significance level at which the null hypothesis cannot be rejected. It is the largest significance at which the null hypothesis cannot be rejected. It is the smallest significance level at which null hypothesis can be rejected, and it is the largest significance level at which the null hypothesis can be rejected. So the significance level, either the smallest or the largest, and whether the null hypothesis can be rejected or can be accepted with the p-value. Okay. The question 4, which of the following p-value will lead us to reject the null hypothesis if the significance level of the test has been defined to be 5%. So the 4 values at which you will find the p-value to be significant would be 0.15, 0.06, 0.025, and the last one is 0.20. So at which of the following would you reject the null hypothesis if the significance of the test is 5%? Okay, and the last one, okay, so this one is really, I just copied and pasted, sorry. So the p-value obtained from a classical hypothesis test is the probability that the null hypothesis is true given the data, the probability that the null hypothesis is false given the data, probability that the observed data were obtained by chance, and the probability of observing the data or more extreme values if the null hypothesis is true. So again, the p-value of a classical hypothesis test is when the probability of the null hypothesis is true given the data, probability that the null hypothesis is false given the data, probability that the observed values were obtained by chance, and the probability of observing the data, of data or more extreme values if the null hypothesis is true. And I can see Priya madam smiling, so I'm sure she would be able to help us with these. But I would still again request all of you to please answer these questions in this format. Write the name, your institute name, and then the numerical in which is the right sequence of answers. So don't send 5 WhatsApp messages. We often get 5 WhatsApp messages. Just send one WhatsApp message with these answers. Okay. So this is with this, I stop my screen share, and may I now request Dr. Priya ma'am to please share her screen and start her tutorial, please.
Yeah, I was smiling because I was so happy I didn't have to take that quiz. So let's try and go to full screen. Yeah, right. Can you see my slides?
Yes, ma'am, we can see your slides. You can see.
Fantastic. Okay, so we'll start, and like last time, we'll stop every 10 to 12 slides the minute I finish one section. Please feel free to type your questions in the chat box, or you can unmute yourself if that's allowed and ask questions. What we're going to be discussing today is the basics of medical statistics. And I'm going to start by saying that I've deliberately not chosen oncology examples because oncology tends to be a little more complicated. So I want you all to understand the fundamentals which are similar across different medical specialties. And then maybe in the next lecture, if there is one, we could focus more on oncology. So this is what we're going to look at today. We're going to start by describing a sample versus a population and understand the differences between the two. A little bit about descriptive versus inferential statistics. Understand what are statistical errors. What do we mean by p-value? And then broadly cover principles of sample size calculation. Okay. Let's start by looking at sample versus population. So this is a very, very basic example. Suppose I want to know the average height of people who are 40 years old in the world. Ideally, I'll have to go out there, find everybody in the world who's 40 years old, measure their height, and take an average. Obviously, that is not something I can do, and therefore, I decide to choose a sample. Now, the sample could be people in a room, it could be people in a hospital, people in a city. So depending on what resources I have, how much time I have, I choose a sample of people and I consider that they represent the population. So whatever result I get from that sample, I assume that it represents the population. And the same thing happens when we do any study. When you run a clinical trial, or you do a prospective observational study, or you collect data from electronic medical records, what you're doing is collecting data on a sample of X number of people, and then you extrapolate that to the entire population. Just to go over this once again, because it's difficult to obtain information from the entire population, we rely on samples to make estimates or inferences related to the population. Now, in descriptive statistics, we describe results in the sample. Okay? We do not make conclusions beyond the sample, beyond the data that we have analyzed. Let's see how we can do that. So, if you have numerical data, a single group of people, and you have numerical data. Now, data is of two types. It could be normally distributed data and distribution-free data, which is skewed data. You would either talk about the mean and standard deviation, right? You would say the mean height of people in the group was 160 centimeter with a standard deviation of 10 centimeter. Or if the data is skewed, then you would say the median height was 160 centimeter with an interquartile range. Or you could talk about categorical data. You could say 60% of people in the group were male, right? 80% of people in the group were non-smokers. So that's when we talk about proportions. So this is, we are just describing the characteristics of that particular sample. This is an example. This was a single group study which looked at adverse drug reactions to terbutaline in obstetric patients. And if you look at the table, you can just see that they've described the characteristics of the, now they use the word population, but what they mean is study population, which is actually the sample, right? So simple means, standard deviations, proportions. This is descriptive statistics. If you have more than one group, you're comparing two groups. So this was a study comparing dexamethasone with placebo for bronchiolitis in children. And the outcome was hospital admission. So if you used a steroid, did it reduce the chances of needing hospital admission? And this is how the results would look, right? In the dexa group, hospital admission was 39% versus 41% in the placebo group. And the difference between the groups was 1.3%. It's negative because placebo group has more and dexa group has less. So the difference is negative, which means in this study, dexa reduced the incidence of hospital admission by 1.3%, right? So this is what we mean by describing results from a study. But having done a study, the question we ask is this a chance finding? So is this finding that dexa reduced hospital admission by 1%, right? Is this a chance finding? Are my results really significant? And if I repeat this experiment, what will I find? Will I find that same 1.3% decrease? Will it be more than that, less than that? So these are questions for which you need inferential statistics. Okay, you extrapolate the results from the sample to the population and draw inferences from the sample. Now, Shubham had a lot of questions on hypothesis, but I have had actually included just 2 or 3 slides on hypothesis because I find that people find it difficult to grasp things in hypothesis terms. Okay, but anyway, for the sake of completion, we need to know what a hypothesis is, and a hypothesis is a statement of belief. So when we do a study, we always start with something called a null hypothesis and something called an alternate hypothesis. Typically, for a study where you're comparing 2 treatments, you start by saying there is no difference between the 2 treatments. So that is the null hypothesis. A is equal to B. Okay, there is no difference between the test and the control. And then you have an alternate hypothesis which states that there is a difference between the test and the control. A is not equal to B. And the goal of your entire study is to prove that the null hypothesis is wrong, to reject the null hypothesis and prove that the alternate hypothesis is correct. So you want to accept the alternate hypothesis. So this is what we mean by hypothesis testing using a null hypothesis and an alternate hypothesis. You want to reject the null hypothesis and accept the alternate hypothesis. There is one other concept known as a one-sided versus a two-sided hypothesis. Okay, look at my previous slide. I have just said that there is a difference between the test and the control. I have not said which one is going to be better. When we do a study, we expect that your active treatment arm will be better than the control arm, right? But you must remember that there is a possibility that the active treatment, the new treatment, the experimental treatment may actually be worse than the control arm. And you have to allow for that. You have to be able to pick that up in the testing. And so in a two-sided hypothesis, we do not specify the direction of treatment effect. We just say A is not equal to B. We allow for both A to be greater than B or A to be less than B. We do not say which one is better than the other. On the other hand, one-sided hypothesis specifies which direction we're looking at. Okay? So we specify that we are only going to look at whether the experimental arm is better than the test arm, the control arm. When do we use one-sided hypothesis? It's in a special kind of study known as a non-inferiority trial, where they're trying to show that a new treatment is not inferior to an existing treatment. Now that is a talk by itself, so we're not going there. But for most of our superiority trials, where we're trying to show that a treatment is better than an existing treatment or better than placebo, we will use a two-sided hypothesis. We will test on both sides to see whether A is greater than B or A is worse than B. I'm going to stop here before I go ahead, if there are any questions.
So madam, there's a question that if suppose the question that I want to prove in my study is that A is equal to B, or if the question is going to be that the treatment is non-inferior, then what will my null hypothesis be? Because that is what the null hypothesis is.
Yeah, so in a non-inferiority study, I'm glad somebody brought up that question. So the null hypothesis and alternate hypothesis that I showed you is for a superiority study. For a non-inferiority study, it changes, it becomes the reverse. Your null hypothesis states that A is worse than B by X amount of margin, okay? And your alternate hypothesis says that A is not worse than B. A is not inferior to B. So in a non-inferiority study, the two just get reversed. Plus, you mention the inferiority margin.
So the null hypothesis remains the null hypothesis. It's just that we change the equations we change.
Yeah, you change the equations. Okay, what you're trying to prove becomes the alternate hypothesis, and the opposite of that becomes the null hypothesis. And in some studies, you may want to show that A is equal to B. Those are known as equivalent studies, right? There, you're trying to show that A is no different from B by more than a particular margin. So A is within 5% of B, either greater than or less than. And there, again, the hypotheses are rewritten in a slightly more complicated way. Typically, most of us will do only superiority studies, and therefore, this is easy to remember.
Dr. Aradhya is asking, will the study design change if the hypothesis is one-sided or two-sided?
It doesn't just change the study design, Aradhya, but it changes your sample size calculation. Because later when we talk about the statistical errors, if you're doing a two-sided test, the statistical error gets distributed on both sides. If you're doing a one-sided test, it stays on one side. And so it makes a difference to your sample size calculations.
And Dr. Goel is asking, if the prior studies show a superiority of the experimental arm, do we still need to go for a two-sided hypothesis testing?
If a prior study is showing superiority,
yes.
Then why are you doing a new study?
Okay.
So if you have enough evidence to show that treatment A is better than treatment B, is superior to treatment B, then what is the basis on which you're doing a new study? So the very fact that you're doing a new study shows that you're not impressed with that evidence, right? And the minute you're not impressed with that evidence, you have to allow for the fact that treatment B may be inferior to treatment A.
So Dr. Goel has rephrased it. Suppose it's a phase 2 versus a phase 3 study, where a phase 2 study has shown that, a new treatment might be better, but now that you are planning a phase 3 study where you're actually comparing with the standard of care, then in that case, the two-sided, how will we do that two-sided study?
So typically endpoints for a phase 2 and a phase 3 study are quite different, right? Phase 2 will have very short-term endpoints, and therefore you will not have evidence related to the phase 3 endpoint from the phase 2 study. And therefore, you cannot comment on whether the phase 3 endpoint is also going to be superior. A good example would be progression-free survival and overall survival. If a phase 2 study shows improvement in PFS, you cannot assume that in the phase 3 OS will be superior. And therefore, in a phase 3, you will have to keep it as a two-sided hypothesis.
Dr. Tiwari has asked, how do we define the criteria to stop a trial early?
Oh my God, that is completely beyond the scope of this talk.
Yes, I agree.
Studies are stopped early either for safety reasons or for futility or for efficacy. Okay, and it could happen either as a planned interim analysis. So typically studies which have large sample sizes, which are going to accrue for a number of years. At the time of writing the protocol, you will build in an interim analysis, which will say that after accrual of X number of participants or X number of events or X time point, we will do an interim analysis, and then statistician will help you to calculate stopping rules. Okay, and what these stopping rules are based on is the study showing early efficacy? Okay, which means you don't need to do the full study because now it's already showing that the treatment arm is superior, and now it will be unethical to continue randomizing patients to a standard arm. Or the other thing is futility. So if at this point there is no difference between the two arms, they will project and tell you at the end of the study what is the likelihood that you will find a difference. And if there is a very, very low likelihood of finding a difference, then please don't waste your resources continuing the study for so many more years. Okay, so that is stopping for futility or early efficacy. The other reason to stop early is if you're finding too much of toxicity on one of the arms, and that's called a safety monitoring. So if you're finding too much of toxicity, that would be one more reason to stop the study.
So, ma'am, is that the role of the data monitoring and safety committee that we have in our IRBs? Is that the role of?
So at least at Tata Memorial, the IRB doesn't routinely do data monitoring of this kind of data. We look at a number of SAEs. We look at whether the SAEs are related or not. And if a particular study is showing too many SAEs, which we consider are related to participation, then we set up a separate independent data monitoring committee to look at the study. A data monitoring committee which is looking at stopping a study should have a very good statistician on board. And our DSMC, which looks routinely at SAEs, doesn't have a statistician on board. So we don't do a data analysis for every study.
Okay.
But we could recommend a data analysis if we find alarming results, alarming SAEs.
Whether the interim analysis is based on a sample size or duration. I mean, will we do it that when we accrue 100 patients in a 500 arm study, or will we do it when we finish 2 years in a 5-year study?
Yeah. So typically it is done based on events, because what you need are events, right? And not just patients or time. So the most common way of doing it is events, though there are ways of doing it at a particular time and at X number of accruals. But patients should have had the outcome, otherwise there's no point in doing it.
Okay. Ma'am, I think we can move forward. There are no more questions at this point.
Right. Okay, we go back to this example, which I'm going to use to explain what are statistical errors. Remember, in this study, we are comparing dexamethasone with placebo for bronchiolitis, and the outcome is hospital admission. Okay. So here, the null hypothesis, as we have stated it, is dexa is equal to placebo, or what we mean is the proportion of patients needing admission in the dexa group is equal to the proportion of patients needing admission in the placebo group. The alternate hypothesis is dexa is not equal to placebo, which means the proportion of patients needing admission in the dexa group is not equal to the proportion of patients needing admission in the placebo group, right? Let's look at statistical errors now. Okay, so the column on the extreme left is the universal truth, right? Which means in reality, there are two possibilities. Either dexa is equal to placebo, or dexa is better than placebo. Or I'm sorry, this should have been reworded as different from placebo. My mistake, right? Study finding, there are two possibilities. Dexa equal to placebo, dexa different from placebo, right? Now, assume that the universal truth is that dexa is equal to placebo, and your study also finds that dexa is equal to placebo. This is great, right? If in reality dexa is different from placebo, and your study also finds that dexa is different, this is also great. There are two other possibilities, that in reality, there is no difference between the two treatments, but your study finds a difference, okay? And this is what we call a false positive error, or a type 1 error, okay? Remember, you're never going to know the universal truth, right? Because you're never going to do a study on the entire population. You are only going to have your study results. If in reality dexa and placebo have different outcomes, but your study finds similar outcomes, it does not pick up that difference. This is what we call a false negative error, or a type 2 error, okay? So the thing is, when we do a study and we get a result, if there is a difference, we need to be sure it's a real difference, okay? And it's not a false difference, not a false positive error. If we do a study and there is no difference between the two treatments, we need to be sure that in reality, there is no difference. And this is not just a false negative error or a type 2 error. Remember that this classification is for a superiority trial. When we talk about non-inferiority trials, all of this gets reversed and the definitions change. So just to go over this once again, type 1 or alpha error finding a difference between treatments where a difference does not exist. Conventionally, we set it at not more than 5%. What this means is if at the end of your study you find a difference, you're 95% sure that it is a true difference, and there is only a 5% probability that the difference occurred just by chance. Okay? This is also known as the confidence. So if your error is 5%, you're 95% sure, 95% confident that your difference is a real difference. And that's where the confidence in a study comes from. On the other hand, a type 2 error or a beta error, not finding a difference where a difference actually exists. And the power of the study is the converse of the beta error. So it's 1 minus beta, which means if there is a difference, what is the ability of the study to find that difference? Now your beta error can be set at 10 or 20%, which means the power of your study can be 90% or 80%. Okay, did you get that? It's 1 minus 100% minus 10% or 100% minus 20%, which is 90% or 80%. Now in this study, they had an alpha or a type 1 error of 5% and a power of 80%. What this means is, so remember that these errors are set, okay, are finalized before you start the study. These are used to calculate the sample size, and they are decided in the protocol before you start the study. So at the end of the study, if you found a difference between the two arms, you are 95% sure it is a real difference. And if there was a difference between the two arms, there's an 80% chance that your study would have picked it up, and there's a 20% chance that your study would have missed it. So if your study ends up with a negative result, it's 80% a true negative, and there's a 20% chance that you missed it because you did not have enough power in your study to pick up that difference. We'll stop here to take questions.
Everybody is still digesting, I think, madam, the type 1 and type 2 errors. So there are no questions at present, but I'm just thinking the very last few statements that you made about type 1 error and type 2 error. No, ma'am, the next slide, after this, that how do we define the type 1 error, that if the difference came out to be within this level, then it is found to be significant. Just those two lines, I think it will summarize the type 1 and type 2 error for us.
Yeah, so type 1 and type 2 error are set at the beginning of a study when we're calculating the sample size and writing the protocol. Okay, and you can read any protocol, and the sample size calculation will always mention what was the type 1 error and what was the type 2 error. What this means is at the end of the study, if you had a significant result, in the sense you found a difference between the dexa arm and the placebo arm, you're 95% confident that it is a real difference, because there's only a 5% probability that the difference could have occurred just by chance. When I explain p-value in the next section, it'll be a little more clear. Also, if you did not find a difference between the two arms, if you ended up with a negative study, there's an 80% probability that it's really a negative study. And there's a 20% probability that you missed finding a difference because of your sample size calculation. Did that make sense?
Ma'am, it did, but can we go a slide back to understand the power in the study? Because that's a question which has come twice now, to revisit the power of a study.
The beta error is not finding a difference when a difference actually exists between two treatments. So treatment A is different from treatment B, but you are not picking up that difference in your study. The converse of this, what is 1 minus beta, is the power of the study, and that is defined as exactly the opposite, right? Ability to find a difference. So if your beta error is 10%, which means there's a 10% chance that you're going to miss a difference, then the power becomes 90%. There's a 90% chance that you will pick up any difference. If your beta error is 20%, there's a 20% probability that you will miss a difference, a true difference. Then the power becomes 80%, which means if there is a difference, you're 80% likely or probable to pick it up.
Okay, I think that's make it clearer, ma'am. Dr. Manish is asking why most of the study have a type 1 error set at 5% and power 80%.
Yeah, I deliberately didn't go into this. So there's been a lot of debate. And you must understand that both type 1 and type 2 errors influence your sample size to a large extent. So ideally, you would want to do a study where there is 0 type 1 error and 0 type 2 error, right? You don't want any errors. But if you were to do the sample size calculations, your sample size would be infinite for such a study, okay? Because all these errors are coming up because we're doing studies in samples and trying to extrapolate or infer from that into the population, right? So whenever you're not testing everybody, there is going to be some difference between the sample result and what you could expect in the true population, and that's where that error comes from. As your alpha error goes down from 5% to 3% to 1%, your sample size will go up drastically. Similarly, as your beta error goes down from 20 to 10 to 5, the power of the study goes up, but at the same time, the sample size will also go up quite radically. So these numbers that I've quoted, 5%, is the maximum by convention. It's the maximum allowable type 1 error. If you are brave and if you have enough resources, you could do a study with a type 1 error of 1%, okay? Which means at the end of the study, if you find a difference, you're 99% sure it's a true difference because you're allowing only a 1% margin of error. But the sample size for that study would be crazily high. Similarly, as per FDA, which regulates pharma-funded trials, 20% is the maximum beta error. Okay? You could do studies with beta errors of 5% or 10%, which means the power of your study goes up significantly. But remember, the sample size needed would also go up that much. The other thing is, why is alpha error kept lower than beta error? In a phase 3 trial, okay, if you find a difference between two treatments, you will implement the new treatment as standard of care, right? I'm comparing dexa with placebo. I find that dexa is much better than placebo, and therefore from now on, all kids with bronchiolitis will start getting dexa. Because my study has shown that dexa is better than placebo, it will become unethical for subsequent studies to continue this comparison. And therefore, a type 1 error becomes important because a false positive results in a change in practice. The minute you find that something is significantly better than another treatment, that becomes the new standard of care. And then subsequent studies tend to get ignored, right? Nobody does future studies. On the other hand, not finding a difference. So I compare dexa with placebo, I don't pick up the difference. See, that is also bad in a way because I'm depriving people of a potentially effective treatment. But at least the possibility exists that somebody else can repeat this study in a larger way and probably pick up that difference. So from the point of view of FDA, from introducing new drugs into the market, a type 1 error tends to be far more important as compared to a type 2 error. And that's why a type 1 will always be less than a type 2. Did that make sense?
Yes, it did, madam. And I think that also answers the question that Joy, Ghosh and Aradhya raised, that why not we keep an error at 1% and make a power of 95%? It's just that it will make the study, your sample size will become very high and might not be possible. So that
yes, it will need that much more resources. So you wouldn't want to do that.
So there's an interesting question that is there any correlation between the power of study and the duration of follow-up and the number of events? And the basic question is if a lower sample size can be compensated with a longer follow-up.
It depends on what the event is. If you're looking at something like overall survival, then Yes, you could. You take a smaller sample size and you wait longer. But the thing is, the longer you wait in a study, it becomes a problem because there is a chance that other things might change. So new drugs might come into the market or something else will change and your question no longer remains relevant, right? And nobody wants to do that. We want to find a quick answer. Because supposing drug A is actually better than drug B, you would rather accrue 200 patients and find the answer in 3 years rather than accrue 100 patients and follow them up for 6 years, because then you're wasting that much time. For that much time, you're depriving people of this potentially effective treatment. So it has to be a play between the two.
So, but what essentially you mean to say is that if we have a longer follow-up, we can effectively reduce our number of errors?
Okay, your errors need a sample size, and your sample in a survival analysis in time to event data is decided by the number of events. So you need X number of events to have the power to detect a difference, right? How are you going to get those X number of events? You need to get Y number of patients. So supposing your event rate is 50%, suppose 50% of your patients are likely to have an event, then to get X number of events, you need 2X number of patients. It's up to you how you want to get those 2X number of patients. Either you make it a multicentric study, you try and find more patients at your own center, or you accrue patients for a longer time and follow them up for a longer time. You could do any of the three. Obviously, the third option would be the least favorable, right? Because your study gets extended by that much longer.
Got it. I think that's the questions we have for the now, ma'am. We can move on to the p-value.
Right.
Just before you proceed, one small little question for me.
Yeah.
So suppose you have a study and you know this is potentially a very good drug, but because of lack of number of events, you're not able to support superiority. So what then you possibly land up crashing a drug which possibly had the potential to change things around. So how do you circumvent that? To give the drug its due, because there are drugs which have been trashed because you were not able to accrue patients, or probably the number of events that you wanted to happen did not happen.
Yeah, that's a difficult question to answer. So as we discussed last time, for some conditions where your phase 3 endpoint is difficult to achieve, for example, prostate cancer and overall survival, there are allowances to use a shorter term endpoint where you're likely to have more events. So you could use PFS or DFS or some other endpoint. Typically, this doesn't happen much in pharma because they have the resources to make it multicentric and to quickly pick up the thing. The other thing you would want to say is, supposing there aren't that many events, right? Is this question worth answering at all? So supposing, you're not finding enough patients or enough events to answer your study question, then maybe the question is not worth answering. So that's a different way of looking at it, because if it's a drug which is being used for a common condition or a condition which is very frequent, then you should be able to do the study too.
Yes, ma'am, I think that answers it. So we can move forward, madam.
Yeah. Right, we saw this. Now we go on to the next aspect, which is understanding p-value, right? So I showed you only half of this slide earlier. I showed you the results from the DEXA group, the difference from the placebo group, okay, the results from the placebo group, the difference between the two. And now comes this word, the p-value, which we all love so much, right? Does anybody want to take a guess on what the p-value stands for?
You can type in, you can't speak up.
Okay, right. So let's go ahead because I know we're running out of time as well. So remember we spoke about type 1 error, which is what we set at the beginning of the study as the acceptable limit for finding a difference by chance. So this is the maximum difference by chance that I will tolerate. It's usually set at 5% or 0.05. P-value is something which is calculated at the end of the study, which tells us, in your study, the difference that you have found, what is the probability that it's not a true difference and a difference occurring by chance? Okay. Now, if you have set your limit at 5%, then your P has to be less than 0.05 to be considered significant. Okay, so P always has to be interpreted in the context of the alpha that you started with. So if Joy was doing a study with an alpha of 1%, he's allowing only a 1% possibility or probability that a difference can occur by chance. He wants to be 99% confident that any difference that he's seeing between his treatment groups is a true difference. And therefore, in his study, a p-value would have to be less than 0.01 to be considered significant. Okay, let's go back and look at this. So here, the first one, hospital admission, there's a difference of 1.3% between the groups, but the p-value is 0.74. What this means is there is a 74% probability that this difference that you're seeing is occurring by chance. Okay, and there's only a 26% probability that this is a real difference. Now, this study had an alpha of 5%, and this is 74%, 0.74. And therefore, this result would not be considered statistically significant. But if you went down, oxygen saturation between the two groups, the p-value is 0.02, which means there is only a 2% probability that this difference is occurring by chance, and you're 98% confident that this is a real difference, which is acceptable, right? Because you want it to be at least 95% confident, and here you are 98% confidence. So the last three values and this value here, all readings less than 0.05 would be considered statistically significant because you started with an alpha of 5%. Before I take questions, I'm going to put in a disclaimer over here. World over, statisticians are moving away from this concept of p-value, and we talk about something called confidence intervals, but that is a separate topic in itself. And Shubham, maybe we need to cover that next time. Okay, so for your understanding, this is what p-value is all about. But please remember, world over, everyone's talking about confidence intervals, not just the p-value. Any questions about p-value?
So can the p-value be more than 1? Is a question.
No, it can't be. It can't be. The maximum p-value can be 1 if there is absolutely no difference between the groups. Okay, your p-value could be 1.
So if I were to put the question of p-value in terms of the null hypothesis that we started with, because most of the quiz questions were related to the null hypothesis. So if the null hypothesis that A is equal to B and we had the alpha value set as 5%, then what would the p-value of 0.01 would read as? I mean, how would we read that statement is that the null hypothesis would be true or it would not be true?
Honestly, Shubham, I can never remember that. Okay, I have a slide somewhere where I have written it down, but that's not the way I remember it. So I find that very confusing. A type 1 error is falsely rejecting the null hypothesis, and a type 2 error is falsely accepting the null hypothesis. That much I know. Beyond that, I don't remember this.
Okay, so it's just trivia then. We don't need to.
It's not trivia. It's very important, but it's very statistical and it's confusing. And so I choose not to remember it, but it's not trivia at all. It's very important.
Okay, so why I asked that question is that when we read a p-value, should we apply it? Because many times when we read a publication, we don't look at the question which is asked. We just go on to the topic and we go to the abstract and we go to the final conclusion. We don't look into the question which is asked. So that is why I think the question that we need to know is important, that what question is being answered, right, madam? Because then only can we imagine what the p-value would signify.
So always look at the method section, which will tell you what was the type 1 error. And then when you're reading, please look at the tables or look at the text and see what was the p-value for what comparison. And the p-value will clearly tell you, based on that type 1 error, whether to accept that difference or to reject that difference. And that's all you need to know. A hypothesis, in terms of null and alternate hypothesis, it's very difficult to remember. Okay? And if you'll attend the next lecture, you'll understand that it's not even about p-value. You'll need to discuss whether a difference is statistically significant based on the confidence intervals for that difference. And so the p-value doesn't really remain important any longer.
Okay. Ma'am, there are not many questions on p-value.
Right. Okay, we're going to quickly go over principles of sample size. I'm reiterating these are only the principles. I'm not getting into any formulae. We should not assume that because we understand it, we can do sample size calculation on our own. You need a qualified statistician to sit with you. But you need to know what information does a statistician need to calculate sample size. Okay, what drives the sample size for a study? Okay, and that's all I'm covering. Zero formula here. Okay, so first, why sample size? If you have too few participants in your study will lack the power. Okay, and you will have imprecise results or confidence intervals, which we will discuss next time. On the other hand, if you have too many participants in your study, you're wasting resources because your question could have been answered with fewer patients. And it's also unethical because again, as your question could have been answered, you were not right in randomizing more patients than were needed. Now, when you're doing comparative studies, right, you need to tell the statistician what is your type 1 error, what is your type 2 error, which means what do you want the power of the study to be, and the expected difference between groups. Okay, so if you're comparing dexa with placebo, you're comparing treatment A with treatment B, what do you think will be the control arm outcome? And what difference do you think will be there in the treatment arm? So the logical question would be, how do we know that difference? Because we haven't even done the study, right? So you could look at the literature. If there are other studies like observational data using the new treatment, smaller studies using the new treatment, you'll get some idea from that. Or you could do a pilot study. And a phase 2 study in that sense is a kind of a pilot study, which gives you an idea of where the results are likely to be going. Okay. Now, we spoke about the power of a study and the type 1 error. Remember, all that was for phase 3 studies, clinical trials. When it comes to phase 2 studies, because we are just doing those as proof of concept, we just want to know, is something likely to work or not likely to work? We no longer stick to the 5% type 1 error and 20% type 2 error limits. You can be a lot more generous. So you will find phase 2 studies with a type 1 error of 20% or 30%, because you just need to get that hint of whether you should go ahead or not. The last thing you could do is, if you know your control arm figure, you could choose a difference which you think would be clinically meaningful. Okay, and that's what this study did. They assumed, so from their hospital records, they knew that there was a 40% admission rate in children with bronchiolitis. Okay, they set 80% power, which means the type 2 error was 20%. They had an alpha of 5%, the type 1 error was 5%. And they decided that the DEXA group would reduce hospital admission rates by 12%, from 40% to 12%, which means 28% hospital admission rate in the DEXA group. And based on this, so this is what it looks like. P1 is 40%, the clinically meaningful reduction is 12%, therefore P2 becomes 28%, alpha and beta, and then you put this into a sample size calculator and you get your sample size, which is per arm. Remember, the sample size is always calculated per arm of the study. And then you will have to add 10% for losses to follow up or protocol deviations. And finally, the statistician will give you a number. So this is the basis on which sample size is calculated. Remember, once again, as type 1 and type 2 error decrease, sample size increases. Okay. As your difference between groups decreases, sample size increases. So if you want to find a very, very small treatment benefit, you will need a very, very large sample size. This was studies with outcomes as proportions, right? 40% and 28%. Sometimes you'll have studies with outcomes as continuous variables, right? For example, a researcher wants to compare 2 drugs for diabetes, okay? And his outcome is postprandial blood glucose level. So this is something which is measured in milligram percent. It is a continuous type of data. And he expects that the new drug will reduce PLBS by 20 mg% more than the standard drug. Okay. Again, 5% type 1 error, 80% power. And this would be his calculation. So he would need to know the mean PLBS in the control arm, the mean expected in the experimental arm, but in addition, he would need to know the standard deviation across groups. So when we talk about continuous data, we need to know the amount of variance which is given by something called the standard deviation, and that is something the statistician will want to know. Okay. So these are examples of sample size calculation for proportional data and continuous data. When we talk about time to event data, which is what all of us would be interested in, how do we calculate sample size? You could compare survival times. You could say survival at 3 months versus, so you could say that overall survival in this group will be 3 months versus in that group will be 6 months. Or you could compare the proportions surviving at a particular time. So you could say the 1 year survival would be 15% versus 25%. Or you could compare hazard ratios. We spoke about hazard last time. Hazard is the risk of experiencing an event. And you could say that if one group has a hazard of 1, how much do you expect the hazard to decrease to in the other group? So 2 or 3 different ways of doing it. Remember, the time to event data is a little more complicated than the 2 examples we looked at of proportions and continuous data, because you need to know not just the number of participants, but also the number of events, the duration of accrual, and the duration of follow-up. And then you may need to account for patients who get censored. So this is something where you definitely need a very good statistician to sit with you and help you to calculate the sample size. Lastly, sometimes we do single arm studies or prevalence studies, right? So you want to do a survey in a population, or you just want to measure the incidence or prevalence of something. Now here there is no comparison. So there's no question of finding a difference by chance or of missing a difference. Here we talk about type 1 error because we want to be confident about our results. So if you find that the prevalence of a particular condition is X, how confident are you that that is the real prevalence? The second thing is, what is that prevalence that you're expecting? Is it 30%, 40%, 50%? And margin of error, how precise do you want to be? So by how many points is your estimate allowed to differ from the true population value? I'll follow this up with an example which might make it a bit clearer. Typically, this margin of error can't be more than 20% of the prevalence. For example, if your condition has a 20% prevalence, your precision will be 4%. Okay? And that's the data you need to put it into the sample size equation. So a researcher wants to carry out a descriptive study to understand the prevalence, that's a typo, of asthma among school children. Now, in a previous study, he found that a prevalence was 40%. So he thinks the prevalence of asthma will be around 40%. He wants to be 95% confident, and he is allowing a 4% margin of error. Okay, this is the info that the statistician needs. Okay, and he gets a sample size of 406. So what this means is a 4% margin of error around 40%. If the true population value of prevalence of asthma is between 38 and 42%, it can be detected with 95% confidence if you were to look at 406 children. Okay. If you finish your study and the true population value was not in this range, it was a different value, then you are no longer so confident and your margins of error would change. Okay. All very complicated, I know. A good statistician should be able to help you with most of this. This is the information that you need to give the statistician. Any questions?
So there's still no question on the sample size calculation, but there was one question on the p-value. So,
right.
So the p-value question was that in a non-inferiority trial, does p-value hold the same importance?
In a different way. In a non-inferiority trial, we always look at confidence intervals. So we look at a one-sided confidence interval. a p-value won't give you as much information as maybe you need to do a separate session on non-inferiority trials.
Yes, I'm just noting down all of these.
Yeah.
So, how much margin of error is a acceptable cutoff in what you just explained, the margin of error that we can use?
So the margin of error or precision is valid only for a single arm prevalence study, and the recommendation is that the margin should not be more than 20% of whatever prevalence you're expecting. Okay, so if you had a 50% prevalence of a particular condition, then you would be allowed a 10% margin of error, which means your sample size should be able to detect values between 45% and 55%. If you had a 20% margin of prevalence rate, then your margin of error would be maximum 4%. But these are just, these are not hard and fast rules. It depends on the study that you're doing.
Okay, okay. Ma'am, there's a question by Dr. Arun Goel. May I invite him to put his question? It's a bit complicated. I might just mispronounce it and miss
yeah, of course.
Dr. Goel, can you just unmute yourself? Hi, sir.
Hi.
Hi, sir.
The question was basically, in some studies, the estimate for the control group value, which has been made, and the final result in the control group, there turns out to be a big difference.
Yeah.
So how the study result has to be interpreted in this setting, and the power of the study, how does it get affected in this?
Typically, what people tend to do is when they start a study, they tend to believe that the result will be much larger than it actually is. And that happens in a lot of study. We want to believe that a new treatment would be grossly superior to the existing treatment. And your point is right, that at the end of the study, you find that the control group has not done as badly as you thought it would do. And the new treatment has not done as well as you thought it would do, right? So if you were expecting outcome rates of 10% and 40%, right? Yeah. You end up with outcome rates of 20% and 30%, which means your difference is much less than what you had anticipated. And the final conclusion of the study is that the study was not powered to detect this difference, and you need a better study or a larger study. And that's something which irritates all editors, because if a larger study is needed, you should be doing that study instead of publishing this paper, right? So there is nothing to be done about it. It just means that your calculations went wrong, which is why for studies which are going to last a long time, it makes sense to have an interim analysis to look at what is happening. Because if your control group is doing fantastically well, okay, and your treatment group is not doing that well, you have two options. Either you examine the study for futility, or you redo your sample size calculations and amend the protocol to accrue that many patients. It's better than going to the end of the study and then saying we were underpowered.
I think on oncology, this is happening recently. Like there are many studies which over on trastuzumab, and the estimates which were based on previous older studies actually went haywire, and the outcomes in the control group have turned out to be much better.
Yes, it would happen because as other conditions improve, I don't know whether your other care conditions are improving, right? So obviously control groups are going to do better and better. So you can't use very old historical data to base your estimates.
Okay. Dr. Gunjan is asking, what's the difference between type 1 error and margin of error? Because both would...
No. Margin of error is used only for a single arm prevalence study. It is better known as precision, the limits of precision. Please don't get confused. Okay. So the margin of error is in a single arm study. When you calculate what is the prevalence in a particular population, what is the range of values? So as I said, if you're finding a 40% prevalence in your sample, you know that in the population, it could range from 35% to 45%. That is known as the limits of error or the precision or the margin of error. Okay? Please don't get confused between that and a type 1 error.
Okay. How to calculate sample size when we are comparing sensitivity and specificity of two tests, where we will not be requiring any p-value or any alpha?
You will still be requiring a p-value. The way to compare is what is the expected sensitivity of your existing test what is the sensitivity of the new test? Okay, a better way of doing it is to combine sensitivity and specificity into a single parameter, which is known as the area under the curve. So you plot a receiver operating characteristic curve. It's known as an ROC curve. And then you calculate the AU-ROC, area under the curve, which is a combined measure of the sensitivity and the specificity of a test. And so you could compare the areas under the curve for the two tests. Again, a completely different talk by itself. But you will need a p-value because there is a possibility that you will find a difference between the two areas just by chance, right? So if you find a difference, you need to be sure that it is a real difference. And you also need to power the study. You need to have enough samples to calculate the sensitivity and specificity. So all these concepts do exist over there also in a slightly different way.
So Joy wants to know that can we recalculate the sample size at interim analysis if we find that it's not going the way we want?
Good question. It has been done. It's not that it's not been done. And so statisticians don't recommend it, but if you're going to be grossly underpowered, then it's a better thing to do. So, yeah.
So we can do that.
Yeah, but see, it'll have to be done in a proper way. It'll have to be mentioned on your clinical trial registration that you amended the protocol to increase the sample size. It'll have to be mentioned in your final publication that you did an interim analysis, because some things I did not cover is the question of multiple testing. So when you look at a data set multiple number of times, you are increasing the possibility of finding a difference just by chance. And that is something known as multiple testing. Okay. So if I was to compare two groups, and so I have a two-arm study, and I compare the two groups after every 20 patients are accrued. I keep comparing until I find a difference at some point, right? The chance of the probability of finding a difference just by chance increases when you make multiple comparisons. And statisticians will adjust for that. So they will adjust the alpha value, the type 1 error, and distribute it between your various comparisons, okay? And so that becomes a problem. So unless you have to do an interim analysis, don't do it. And if you do an interim analysis, make sure the overall type 1 error of the study remains at 5%.
Okay. Dr. Manish wants to know that how do we need a sample size calculation for a pilot study?
Sorry, how do we?
Ma'am, do we need a sample size for a pilot study? How do we calculate the sample size for a pilot?
Yeah. So if your pilot study is a formal phase 2 pilot study, okay, you will need a sample size. So a phase 2 randomized study will need a sample size. Sometimes we just do a single arm pilot study. For example, I'm comparing a new antiemetic with ondansetron for post-op nausea and vomiting, and I have no data on the new antiemetic. So I'll just take a convenient sample of 20 or 30 patients and see how many of them vomit. That will give me a very, very rough estimate of what to expect. But remember, this could go wrong. Maybe the first 30 patients were patients who were anyway prone to nausea and vomiting, right? So there are going to be problems with that, but it's a quick and dirty way of getting some initial data.
Okay, ma'am. I think that's all the questions that we have. Some have been answered within the group itself. So there was a question on confidence interval which Caleb asked, and I want to assure Caleb and everybody else that that is going to be a next class, and we will cover odds ratio and the risk ratio and the confidence interval, and if we can cover the forest plot as well. But I think that will be sometime a month later, madam, sometime at the end of September, I think. Just a month, 4 sessions we'll have in between. Okay, so I think we have had a wonderful session, and it makes a lot of things much clearer. But again, like I said, that it needs to be visited again and again and again, and that is why this video is recorded and available on our YouTube channel, Cancer Academy, for references. I don't know why I'm getting requests for a Kaplan-Meier class. The Kaplan-Meier class is already, we did a month back, and that was our the first session we had with madam, and it's there on our YouTube channel, so you can go and visit that, and it's a wonderful lecture. So before I let madam go, I want to go through the answers of these questions, because I think some of them need to be explained by madam now that we are
Once on hypothesis, I'm very sorry, but I won't be able to explain it. I'll try, but I won't be able to explain it in hypothetical terms.
If you tell me it's not important, I will not.
No, again, you're getting me wrong.
If I get it, I get it. It's important,
Yeah,
but again, sorry, I just put it again. That so, Dr.
Yeah,
Geeta, can you come in and tell us about the quiz? How many participated till I get the quiz thing on? Dr.
Yeah,
Geeta?
so today, although the participation has been phenomenal again, you know, we've had more than 100 participants, but the participation in the quiz was limited to 12. I think, you know, statistics still scares most people away, but yeah. But I think, you know, if you were to do a quiz at the end of all the lectures and probably a redo on it, maybe, you know, you'll get more participation on the quiz as well. So we had only 12 people answering the quiz question, and none of them got it right. So I'll just leave it at that. So all right, we don't have any, but yeah, 3 people got 4 right. So Shubham, you can, yes, go over the questions.
Okay. So the first question was that how do we define a type 1 error? So again, this definition is in relation to the null hypothesis, and that is why probably I got swayed that, you know, we need to define the null hypothesis.
Okay, Shubham, if I can just come in here, this is actually the correct way of defining a type 1 error, because this applies irrespective of whether you're doing a superiority study or a non-inferiority study. What you're doing with a type 1 error is rejecting the null hypothesis and accepting the alternate hypothesis. The only reason I did not use this is because as clinicians, we find it difficult to understand what is the null hypothesis and remember it. And therefore, I put those things about finding a difference by chance. But please remember that applies only to a superiority study and not to a non-inferiority study. So technically, this is the absolute right definition of a type 1 error. Rejecting the null hypothesis.
So this is how we would define actually a type 1 error,
Yeah.
that we would reject a true null hypothesis. And in a similar fashion, the type 2 error is when we do not reject a false null hypothesis. So that is how we define the type 1 and the type 2 errors. Now the p-value. So p-value of a test is defined as the smallest significance level at which the null hypothesis can be rejected. So I think the significance level is the one that we define with the alpha error, madam. If that would be, how would we say the smallest?
I'm just trying to understand whether the answer here is smallest significance level or the largest significance level at which the hypothesis can be. Okay, I'm getting confused with this. I suppose it must be right.
Okay, so the answer is smallest significance level at which the null hypothesis can be rejected. And which of the following p-value will lead us to reject the null hypothesis if the significance level?
This is fine.
So it's again less than 5%, which would be the answer. So this is 0.025. Okay, and the last one is that the p-value obtained from a classical hypothesis test is the probability of observing the data or more extreme values if the null hypothesis is true. Again, I think I just...
Again, this is the absolutely conventional way of describing the p-value. What I told you, the probability of finding a difference by chance is for a superiority study. But I find that when people hear that, they tend to remember it better than this. But this is the true statistical definition of a p-value. So I'm sorry if it's been a bit confusing because these definitions are a bit different from what I've said. But
this was our answers that we were looking for, 2, 3, 3, 3, 4. But thank you, madam. Thank you once again for such an engrossing talk. I think we have had very senior faculty. Dr. Vijay Hari Bhakti was there. I think Dr. Manomoy Gangli was there. He had logged in initially. And obviously, Dr. Arun Goel, he's the head of our department at Max Speciali. He's there. So thank you so much, ma'am. I think it's a great pleasure to hear from you again and again. And we are thankful that you are taking our next class on confidence interval, and I'm sure it will open our eyes to a lot many things. And then I would request, probably, ma'am, you had suggested that we should learn how to critique a paper, and we could have probably a month later something, you can provide us with that ideal paper and all of us could go through it, and then probably we can have how to read it. So that would be, I think, the icing on the cake to finish with statistics at least, madam. I think that's
sure.
Sure.
Sure. Thank you so much.
Thank you, ma'am. Thank you so much. Thank you, everybody, and good night. And we'll see
Thank
you
you.
next Wednesday. We'll announce the class that's to be done in next Wednesday in the subsequent week. So thank you so much. Okay, good night, everybody.
Thank you all. Good night.
Good night.